For the last few years, the electric vehicle arms race has looked predictable. Bigger batteries, faster charging, more range. Tesla pushes software and efficiency, BYD pushes scale and cost. Everyone else tries to survive between those two gravitational forces. And then, almost quietly, Mercedes makes a move that doesn't look loud until you understand what it changes. Not a new screen, not a new platform announcement with fireworks, a motor. In July 2021, Mercedes didn't partner with a motor startup, they acquired one outright, a UK-based company called YASA, specializing in a motor geometry most automakers had avoided because it's difficult to manufacture at scale. Then came confirmation. This technology would be integrated into upcoming Mercedes EV platforms. This is the story of the YASA Axial Flux motor, and why a component most people never see could reshape what an EV can be. In the EV world, attention follows the battery. It's easy to measure, easy to market, easy to compare. But engineers don't build a car around a battery alone. They build it around the full energy chain. Battery to inverter, to motor, to cooling, to control software, to drivetrain losses. And if one link gets dramatically better, the whole system changes. Mercedes' acquisition of YASA isn't about a minor efficiency tweak. It's about power density, how much power you can produce per kilogram and per liter of space. Because in an EV, space and mass aren't just packaging problems. They are range, handling, cost, and design, locked together. So the real question isn't, is the motor powerful? It's, what does Mercedes gain if the motor becomes smaller, lighter, and still meets performance targets? And why would that make competitors pay attention? To answer that, you have to understand what YASA actually is, and why Mercedes wanted to own it entirely. YASA doesn't fit the usual EV supplier narrative. Founded in 2009 as a spin-out from Oxford University, it didn't begin as a mass production giant chasing quarterly wins. It grew out of an engineering-first environment, closer to a lab mindset than a marketing department. And from early on, YASA focused on one obsession: maximum torque and power in the smallest, lightest package possible. Not good enough for most cars. Not cheap at scale first. High performance first. Because if the physics works there, you can adapt it later. That's why YASA's motors showed up in demanding, low-volume applications where every kilogram matters and every thermal weak point gets exposed. Hypercars, motorsport, aerospace prototypes. Then, in July 2021, Mercedes made the acquisition official, reportedly paying in the range of £50 to £70 million. Not a licensing deal, not a minority stake, full ownership. Because when a legacy manufacturer bets on a motor architecture that's difficult to industrialize, it usually means one thing: they don't want to rent the future, they want to own it. Most EV motors people picture, whether they know it or not, are variations of a radial flux design. They're typically cylindrical. The magnetic flux moves outward from the center, and the layout has decades of manufacturing momentum behind it. Axial flux is different. Instead of a long cylinder, think of a flat disk, a pancake geometry. The magnetic flux is oriented along the axis of rotation. This isn't just a design novelty. That geometry can enable significantly higher power density. Some axial flux designs claim 2 to 4 times the power density of comparable radial motors, though real-world figures vary depending on cooling, materials, and application. Still, the directional advantage is consistent enough that it changes what's possible. Packaging flexibility. A flatter motor can fit in places a longer motor can't, between wheels, within tight chassis constraints. Mass reduction. Less motor weight reduces overall vehicle energy demand. System-level opportunities. If a drive unit shrinks, designers can rethink cooling paths, suspension packaging, cabin space, even crash structures. Mercedes isn't alone in noticing. Ferrari's SF90 Stradale uses axial flux motors, sourced from a different supplier, to power its hybrid front axle. Koenigsegg has explored similar geometries for its hypercars. So the technology isn't theoretical, it's proven in limited production. But here's the part that matters for the mystery. If axial flux is compelling enough for Ferrari and Koenigsegg, why didn't everyone adopt it? Because the catch isn't the idea. The catch is making it reliably, over and over again, at automotive scale. In high-performance electric motors, tiny imperfections become big problems. Axial flux designs can demand extremely tight air gaps between rotating and stationary components, sometimes less than a millimeter, maintained across the full disk surface. Precise alignment across flat rotor/stator surfaces, where any warping under heat or stress creates efficiency loss or mechanical interference. Robust thermal management, because high power density means heat builds fast. If you don't move it efficiently, performance drops, or worse. And heat isn't just a performance issue. Heat is efficiency loss, component aging, and in worst cases, reliability risk. So axial flux is a manufacturing test as much as it is an engineering concept. Radial flux motors have had decades to optimize tooling, quality control, and supplier ecosystems. Axial flux is still climbing that curve, which is exactly why Mercedes' involvement is significant. A company like Mercedes doesn't build its future on a motor design it can't validate, cool, control, and service at scale. So when they move from interesting technology to full acquisition and confirmed integration, it signals confidence not only in performance, but in repeatable production. And now the story shifts from impressive motor to the real investigation. What does Mercedes actually want to do with it? Mercedes has a long history of treating the drivetrain as identity. In the combustion era, it was engines and transmissions, in-house designs that defined each model line. In the EV era, the equivalents are motor technology plus power electronics plus software control. If you outsource that core, you inherit everyone else's constraints. Supplier timelines, supplier margins, and the risk of being technically matched by competitors buying from the same catalog. The YASA acquisition is about control. Control over the motor's performance envelope, peak output, sustained output, thermal behavior. How it integrates with the inverter and cooling system, and how it differentiates the driving feel, quietness, smoothness, response, repeatability. Because luxury in EVs isn't just leather and screens, it's the invisible stuff. How instantly torque arrives, how stable it feels at sustained high speed, how consistently it performs after repeated acceleration runs, and how the system manages heat without the driver ever sensing a limit. This is where axial flux becomes more than a spec sheet. It becomes a lever. And once Mercedes pulls that lever, competitors face an uncomfortable question. If Mercedes can package more performance into less mass and own the technology outright, what happens to the current competitive order? Tesla's brand advantage has always been tied to the perception of technical leadership, especially in drivetrain efficiency and software-driven performance. If another major manufacturer delivers a noticeably different performance profile, high torque density, compact packaging, strong thermal consistency, Tesla doesn't automatically lose. But the narrative shifts. And in technology markets, narrative affects demand, talent acquisition, and investor confidence. Neither Tesla nor BYD has publicly prioritized axial flux development, at least not yet. Tesla continues refining its permanent magnet and induction motor strategies. BYD focuses on vertical integration, battery cells, power electronics, and cost optimization at scale. But an efficiency gain from the motor side pressures both strategies, because if you can extract more performance from the same energy, you can potentially meet range targets with smaller batteries, reduce cost pressure on the pack, and improve real-world usability without increasing vehicle mass. In other words, axial flux doesn't just threaten performance bragging rights, it pressures the entire equation of weight to efficiency to battery size to cost to design freedom. So even if competitors don't respond with their own axial flux programs, they'll have to respond somehow, whether through battery chemistry, software optimization, or alternative motor improvements. The question is whether Mercedes moves fast enough to set the benchmark before others catch up. Which leads to the next question. If this is real, where does it show up first? Not in theory, on the road.
Mercedes doesn't typically debut new high-risk technology in its most price-sensitive vehicles. It validates first where customers pay for performance and tolerate early adopter trade-offs, margins allow iteration and refinement, and the brand benefit is immediate. That points to the performance side of the house. AMG variants and high-output EV architectures, likely including the upcoming AMG.EA platform designed specifically for high-performance electric models. Because if you can reduce drive unit mass and maintain or increase output, you don't just make the car faster.
You make it feel different. More agile in transitions, more responsive to throttle inputs, and potentially more repeatable under sustained heat, fewer derates, more consistent lap times. Then, if the manufacturing and durability story holds up over real-world validation, the technology can cascade downward, exactly the way many automotive innovations have historically moved, from flagship to volume. But none of that guarantees it becomes affordable quickly, which brings us to the part most viewers actually care about. New motor technology always arrives wearing a price tag. Precision manufacturing isn't free. Neither is new tooling, validation testing, or retraining service networks. So in the near term, axial flux advantages are most likely to appear where the business case closes first. Premium EVs, performance trims, flagship models that can absorb development cost. But the downstream potential matters. A more power-dense motor can contribute to lower overall vehicle mass and better efficiency in certain driving conditions. That translates to either more range from the same battery or the same range from a smaller, lighter, cheaper battery. Over time, if production methods mature and volumes grow, costs typically come down, just like ABS, stability control, and lithium-ion batteries themselves. The important point is this. Even if most drivers never learn the words axial flux, they can still feel its effects. If it helps manufacturers hit range and performance targets without simply scaling up battery size. Here's the insight that often gets missed in component-level coverage. The motor isn't the product. The platform is. A compact, high-power-dense motor isn't valuable only because it posts impressive numbers on a dynamometer. It's valuable because it gives vehicle architects options they didn't have before. Different crash structure geometries, different cabin proportions, different suspension layouts and weight distribution, different cooling strategies, and different performance targets, without ballooning the battery to compensate. That's why Mercedes' move matters even if you never see the motor. It's a quiet architecture shift. And architecture shifts are the moments the industry remembers, often years later, when everyone else suddenly looks late. The original Tesla Roadster didn't change the industry because it was fast. It changed the industry because it proved a different architecture was viable. Mercedes is betting that motor technology is the next architecture lever. So where does this leave us? Mercedes has acquired the technology, confirmed integration into future platforms, and begun the hard work of scaling production. But acquisition isn't the finish line, execution is. If Mercedes successfully industrializes axial flux at meaningful volume, three things become worth watching. 1. Thermal consistency in real vehicles. Not peak power numbers, repeatable power after heat soak. How does the motor perform after 5 hard launches? After a sustained mountain climb? After 20 track laps? 2. Packaging choices on new platforms. Where the motor sits, how vehicle proportions change, what space gets freed up. If new Mercedes EVs look or feel fundamentally different inside, that's the motor making itself felt. 3. Competitor response. Not press releases, actual product decisions. Do we see Tesla, BYD, or others announce new motor architectures? New supplier acquisitions? New manufacturing investments? Because the next phase of EV competition won't be won by a single headline number. It'll be won by the companies that redesign the entire system around better fundamentals. And Mercedes is signaling, quietly but clearly, that it intends to be one of them.